Everyone knows who participated, and I don't know that that'll do much for you, but you know, at least they'll log that in. Oops, look out. All right. So I don't know that all of you know who Noreen and I am, but I'm Fran Sharkey. This is Noreen Beresford, and Noreen and I prepare the majority of the piping specs that come out of the Conshohocken office. So we'll start with our safety minute, just to get that off the table. I'm sure everybody's noticed the past couple of days, everybody's back to school. We have the flashing, speed limits through our neighborhoods, our school buses. We had somebody yesterday delayed coming into work because school bus broke down and they had to offload all the kids from one bus to the other. So just keep it in mind, follow the rules, pay attention, be a good neighbor, take care of the kids, and allow a little extra time in your commute, to take into account that the next couple weeks is always a little rocky. So today's topic is piping specification basics and the service pipeline identification. So has everyone in here worked on P&IDs? Just, okay, good. So we'll get into, this is what we're hoping to cover today. So we're going to go through a few service pipe identifications that you're familiar with. We'll do one for a client, one for Jacobs. And we're going to relate that to the work that you do on your drawings to what Noreen and I do. So we'll jump you over to the piping service index, the insulation index. We'll give you an understanding of what is in a pipe spec, how our Jacobs numbering works when we don't start with the client spec. And then Noreen's going to jump into, there's a lot of things in a spec, but sometimes certain things are preferred. And certain things you're going to see on a P&ID more than other things that would be in a spec. And she's going to walk you through that. And then we're going to get into, some of the real familiar P&ID symbols you use every day, but what's that actual component look like? I'll give you a little hands-on, because I've gotten comments from people who've been in the business for 10, 20 years. I draw this every day, but I've never actually seen one or held one. So you have that opportunity. So hopefully, if you have questions, raise your hand along the way, but, just follow along and go from there. Okay, so this is an example. You have this on all your lead sheets. This one is a client example. Any of you worked on AbbVie or Hospira, this is going to look very familiar. Okay, our first line is our line size. Our first number is our line size. Then we have our pipe service designation. This is clean steam in this case. We have our pressure. That's not always filled in, but on clean steam we care about the pressure. Okay, 200. That's the AbbVie or the Hospira pipe spec. So PS 200 is the pipe spec you would go to find all those components. They have a unique 7-digit line number that only appears on the one line. And then they have a 3-digit insulation code that tells you the thickness of the insulation that's appropriate for that service, for that pipe size. It tells you the insulation material, that's the 052. For example, it's fiberglass insulation on this pipe. And the last digit they have is the jacket. Sometimes we want a jacket over the insulation material for abuse protection or for cleanability. That happens to be a PVC jacket. So how's that relate over to our documents? So we have a couple of service indices. Are we out of order? I think we are out of order. I'm going to jump. Okay. We did one out of order. Okay. So this is our hygienic service indices. And this was specific for the AbbVie job. So we'll do a little, the service indices covers every pipe service you have on the job. It tells you what the service designation you're going to see in the line number is, what the material is, and a lot of other information that is information for the contractor. You're welcome to understand it, but maybe it doesn't concern you in your daily day-to-day job.
So what's a service index? So a service is, say, the different type of thing, like chilled water or steam or condensate. So that's the actual fluid that's actually in the line.
Yeah, so one place where the contractor can look to say, okay, my chilled water pipe or my clean steam, let's use our same example. My clean steam pipe with the designation STM CLN that you saw in the line designation is going to follow pipe spec 200. You could get further into it and to care about how it's going to be tested. It all is told there, but for the purposes of today, this is what we care about and how it relates to the line designation. Then we jump into the insulation index. That's our 15083. I'm telling you these numbers because you might be on a job where you're in JPI and you might care to look. Something doesn't look right on a P&ID. Did the process engineer get that wrong, I'm gonna peek at what I think it might be. So those are some of the reasons we're trying to also tell you, these are the things that are out there. But for our example, clean steam, we were at 25 PSIG, okay? That in the 6-inch size that we had was gonna have a 1-inch thick insulation. It was using the material, cellular glass, 052, and the PVC jacket, okay, the 101. So that's an example of how one of our clients does it. Where, who gets it, do you mean? Okay, so on a job for the pipe specs, all of our specs go to the piping subcontractor.
Gotcha.
And that is included in various scopes of work. So depending on, the hygienic, the one we were just talking about, might go to the hygienic piping subcontractor. He only is concerned about the ones that are at a higher level of cleanliness. And then we have the non-hygienic, who might do everything from the plumbing through the HVAC type utilities.
So the service index is also one of the first things that Brandon and I do. You get with a client and you talk about this, and you build this document, and this document is then used by the process group to end up filling out the P&IDs that you guys want.
Right.
This is all has to be agreed upon beforehand so they can start doing their.
So when we get stuff that has like, XX, because they don't have necessarily the information yet,
Right.
once that's been finalized.
They have to get this,
they
they
wanna
review,
use
they
that.
get that
Right.
populated, and they populate it to you.
Exactly. And we have a starting point. We have masters. So when we start a job, we give over our masters to the process engineer and say, highlight what you think we need. There might be 10 different appropriate materials you could use for a spec, but based on economics, we might say, okay, this, in this country, this is what we think you should use. And that's how we arrive at PS 200 or insulation material 052. That, and also understanding what the owner's preferences are.
There's owner's preferences, there's conditions that apply, say, to a certain country. So when they put this base document out, they go through a full review process to make sure that whatever's on here is in alignment with the requirements of the country.
Right, so I guess, is there like code requirements of what something should or should not be, or no?
Yes, there is.
There is,
Yeah.
so it's
And
not
that
someone's
all-
opinion,
That all
it's,
gets considered in that document.
Well, to an extent, there could be more than one choice that's code compliant, and then you can have a preference there.
right.
If something isn't applicable by the code, we won't let them say
Use
that's
it.
my preference.
Gotcha.
Okay. Okay, so this is an example of the Jacobs numbering system that you would see on a lead sheet. So if you come in, you're a client, you don't have a set standard or piping specifications or a lead sheet that is standard. Jacobs has a designation that we start with. So it's very similar, a little more abbreviated than what the Advie and Hospira one was, but it again has the line size, it has our pipe service designation, the unique 7-digit, piping line number, system, subsystem, and line number all together. This number, BBG01, that's our Jacobs pipe spec number. That's for a carbon steel spec. In our example, we'll use that throughout today. That's our example for a chilled water piping system. The last one, CC, is the insulation service. It really is more like the insulation application. This is being insulated for cold conservation. We don't get into telling them it's this thickness, it's this material. They'll go look at that in the spec. We tell them why it's insulated so they know what to look for when they get to the spec. It's a little more simplified, and if things changes along the way, I think it has its advantages because it's a little less rework if anything changes. And these are just what those insulation codes are: anti-sweat, cold conservation, heat conservation, personnel protection, vacuum jacket. And then if it's trace, say it's outside and we're worried about it freezing, we'll say, okay, it's going to have electrical tracing on it besides the insulation, and that would be reflected in the line number. So this is, just doing the same thing. We jumped a little out of sequence here. So this is our service index for the chilled water, same thing what we just said. Chilled water, and then our abbreviation that we saw in the line designation, and BBG01. Okay, so we're going to jump up a little. Apologize for that, guys. Okay, how does Jacobs do their numbering? Okay, so if we're starting with the Jacobs spec, say you worked on Advie, PS 200. That doesn't tell you anything about the material at all. It's an arbitrary number. You have to actually get the pipe spec out. We try to use our number to give you a little bit of knowledge about what that material is. So BBG01 is our carbon steel or black steel material. The next is the flange class. So B, it's a class 150 flange, okay? The next is our type. It's just a general service. There's nothing special about it. It's not hygienic. It's not pre-insulated. It's not double contained. It just gets a G. And then we have an arbitrary number. So this, if you see on a line, XXG, oh, that's stainless steel. So it's helpful than just having these arbitrary numbers that are very client-specific that you might not have a feel for. So we hope that this actually brings a little more clarity to a job. Okay. The next thing we have is, what does a pipe spec include? So Noreen's got a pipe spec example here. This is, again, BBG01. But the things that a pipe spec includes, it includes the pressure and temperature limits of the material. It tells you what the piping material is, carbon steel, for example. It tells you what the fitting material is, if it's a threaded fitting, if it's a welded fitting. It tells you the preferred joint type. Again, is it a socket weld joint, a butt weld joint? It tells you what flanges are appropriate for the spec. If we're in a job in the United States, the ASME flange, or maybe it's a job in another country where we're using a PN flange. So that would be called out in the spec. And then the valve preferences. You could have, 4, 5, 6 different valve choices in a spec, but they're maybe not always appropriate. So at this point, I think I'm going to hand it off to Noreen, and she'll tell you more about what's preferred, what's appropriate, and get into those details.
Okay, so I've highlighted just a couple of things in each of the pipe specs. So the pipe spec, like Fran said, that we're talking about today is BBG01. So the first thing that I highlighted is the fact that it's carbon steel pipe material. And I guess before I start, I should have told you that this here is just a table that we put together. It's a tool. It's never issued. You will never see it in JPI. But it's just our preferences for, just through our experience, what we found. It's also, it summarizes each of the material specs, but it's also, because each of the material specs has more components in there than we may necessarily need, it's the preferences that we would use. So
It's almost like a nice cliff notes to the spec.
I don't know if they know what cliff notes are. But okay, so the first column is the material, and sure enough, if you go look, the first highlighted item, it tells you that it's carbon steel pipe. Carbon steel pipe's a good material. We can use it for cold services, chilled water in this case. You can use it for hot services. You can use it for steam. The bad thing about carbon steel is that it rusts, so we would never have it exposed in a clean room. When we create our material specs, we're creating them based on the application to make sure it'll work, but also economics. So chilled water would work in carbon steel, so that's why we do choose that. The second item is the joints. So for the small bore piping, 2-inch and smaller, we're using threaded joints. Usually for smaller joints, the two main options are socket welded and threaded. When you have a threaded joint, you just need a pipe fitter. They can install it. If you have a socket welded joint, you need somebody that's a certified welder. The bad thing about threading is it might leak. So you would never have a hazardous chemical in a threaded joint. But for chilled water, not that we're hoping it leaks, but if there's a drip here and there, it wouldn't be the end of the world. The larger sizes, for large bore, we have butt weld. And that's where we have two pieces of carbon steel pipe. They come together at a 37.5-degree angle, and they weld them together. And if you look here, it says that we have it butt welded or flanged. So this is just set, this still agrees with this. Our preference is every fitting and each piece of pipe are butt welded together. But let's say we were going against a piece of equipment. It's very, very rare that you would ever weld to a piece of equipment. So in that case, we have to flange. We always put a mechanical joint against a piece of equipment, or 99.9% of the time. So we could either thread a nipple into a piece of equipment, or we could flange against a piece of equipment, or in a hygienic service, we would have a hygienic clamp against a piece of equipment. Third item here is block valves. So the three most common types of block valves in non-hygienic services are gate valves, ball valves, and butterfly valves. And sure enough, in this specification, we have all three. So you have to figure out which one we want to use. That's why we have this table. Small bore, we're using ball valves. Pretty much in gases and in water services, we like to have a quarter-turn block valve. And that's what a ball valve is. And I'll show you a sample in a little bit. For the larger sizes, we're using a butterfly valve. So, let's see, I have to write notes down. So like I said, these specifications have a lot more items in here. You'll see other valves in here too. But everything we need to design and build a chilled water system will be in here, but there might be other things also. Let's see. I'm going to throw out this. Okay, so here's a P&ID example. And we talked about block valves. So block valves are isolation valves. You're just stopping the flow. So here we have a ball valve, 3/4 inch size. It's appropriate for this BBG01, just like we talked about. It's a drain valve, so they have a nipple here and a cap. They only open it when they want to take the cap off and drain the system. Here's a butterfly valve on a 3-inch line, perfectly appropriate because it's 3-inch and larger. We want to have butterfly valves. Here we have block valves around a piece of instrument in case they need to service that instrument. So now let's say, oops. Let's say the engineer decided that they marked the P&ID like this, and they wanted to change the 3-inch to 2-inch. Is there anything else that needs to change? There you go. So you know, okay. So right, so the butterfly valve here needs to go to a ball valve. So that's where that tool would come into play. But you could also look elsewhere on the P&ID. Also, if you were to go to this material spec, you're not going to see a butterfly valve in the 2-inch size. So that's where you have to remember that what you're doing is, I don't know about this.
I invited myself.
This is where you have to realize that you are the first level of quality for the office. What you're doing is, it's very important. And if you see an error like this, you just need to raise your hand and tell the engineer that what they have on the P&ID, just check them, in a nice way. So I think my next is really just my components here. So, like we were just talking about block valves, the 3 most popular types of block valves in a non-hygienic will be
So while she's collecting up her samples, the pipe specs that you're looking at and all the components that they're doing, when they develop the pipe specs, they then get downloaded to our 3D programs so that these components are available. So that's what they do, then they transfer that into a physical piece that we can actually work with and design.
Okay, so we were talking about block valves. Block valves are known as isolation valves, and just like we were talking about here, we have them at drains, we have them around pieces of equipment. If you need to service them, you have them around instrumentation. So this here is a gate valve. It's blocking the flow. When we lower the gate down into the seat, you can't go through it anymore. It's a multi-turn valve. The nice thing about gate valves, they're in small sizes and large sizes. If you had to pick a service that you're going to use a gate valve a lot, steam condensate. It's used in others, but probably wouldn't use a brass one in steam and steam condensate, but this is a gate valve. It's just isolating the flow or blocking the flow from going down. Here's a ball valve, and then this one's a ball valve too, which is a little nicer because it has a cutaway. So this is a 1/4 turn valve. Okay, we just need a 1/4 turn to block the flow. If you look downstairs, probably near your washing machine, you probably have them on those lines. It's just a ball with a hole through the center that the flow goes through the hole, goes through the cavity, and then we block it when we turn it off to the side. So this is a brass one or a bronze one. This is a stainless steel. It's a hygienic one. We'll talk about these ends in a little while. Butterfly valve. So it always goes hand in hand with the ball valve. The ball valve would get extremely heavy if we had to have it in larger sizes. So then we come to the butterfly valve. The butterfly valve has a wafer inside. Again, it's a 1/4 turn valve, and we just close it and we open it. I don't know if I'll pass this one around
And
just
that
because.
gets installed in between 2 flanges.
Yes.
And it comes in 2 types. One is a pass-through, and the other one's gonna end up having lug type if you have to end up putting it.
Right, a wafer and a lug.
So I always call it almost as I call this almost like a daisy. So this, we have a flange on one side. The flange is going to be too big. But imagine we have a flange on one side, and the holes match up. And you bolt it through. So this is lugged because it's actually tapped. And then what Steve's saying is there's a type called a wafer. So there's no holes here, and it just is sandwiched in between the 2 flanges, and the bolts hold it in place. You may say, well, why would I want to use that? Well, it's going to be cheaper. It's also going to be a lot lighter. So when you get to the large sizes, sometimes you're worried about weight.
So the other piece that she's got on there, there's an extension stem you can see, the green piece that's sticking straight up.
I don't know if that, or is that just
Insulation.
standard? Oh, okay, well, all right, we'll go there. So the nice thing about the gate valve, we're going to pretend this is a gate valve. It's not, but we're going to pretend because it just looks like it over there. So the nice thing about gate valves is if the line is insulated, that's what Steve is saying. Usually when you're wrapping the insulation over, the insulation will go up to here. We can still operate the valve. no problem.
Your fingers won't hit the insulation.
So the insulation will be up to here. We can still operate the valve, close it, open it, not a problem. When you get to ball valves and butterfly valves, not so much the butterfly, but a lot with the ball, but we do have to investigate with both. We just have to make sure that the insulation is not going to go into the area where we need to grab the
Yeah.
handle.
Hold it. You can see that handle, if the valve is insulated.
Yeah, so even in a small, very thin insulation, his fingers are gonna hit the insulation if he tries to turn that.
So what there's some manufacturers that will put a stem extension like this. And then we can clear the insulation, so we can adequately wrap our insulation around our pipe, and we won't be knocking it back and forth. We insulate for a couple of reasons. We insulate for heat conservation. If the line is hot, we want to keep it hot, but we also don't want to be burning ourselves. Number two is if it's for cold conservation, we're trying to conserve the cold, we're trying to conserve the temperature of the line, but it's going to sweat, just like a can of soda is going to sweat if that barrier is broken. So we really want to make sure that that insulation barrier stays intact around the valve. Globe valves. Another reason we use valves on the P&IDs is for regulating. So whenever you're drawing an instrument and you have two block valves, you have your instrument in the middle and you have a bypass, you put a globe valve, this is a globe valve. It looks a lot like a ball valve, however, it's different inside. It's a little bit more of a bulbous or rounded here.
Do you want to have their P&ID symbols up? They might
Oh,
be able
yeah,
to
I'm
see.
sorry, yes.
So like you can see that it's drawn a little differently on your P&ID.
So this is your globe. So we just went through the gate, the ball, and the butterfly. So this is a globe valve. So you can, again, it's quarter turn. Just like the gate valve, it goes from small sizes to large sizes. It crosses a lot of services. And probably the most popular place that you'll see it would be around bypasses, around instrumentation. So this I don't have a sample of, but this is a balancing valve, which you see a lot on P&IDs. That's really a fancy globe valve. That's probably the best way to describe it. They have these two little ports on it, so that's why it does look like a globe valve here, but they have these two ports on it where we can hook instrumentation up to it. So they're using that to measure, keep the flow in check for usually the HVAC systems between the supply and the return. So if we have to regulate the flow, whether, either things were added or things are shut down, or just when the start of the building, there we can actually plug meters into it to check the differential pressure across it to make sure that we have the adequate flow. And there's some tables and things like that come with it. I'd have to do some more reading on it, but it's really just a glorified globe valve. The third reason we have valves is a check valve. The check valve is really just making sure that your flow is staying in check. Your flow is continuing on the way that it's intended. It's not allowed to come back. When do you see check valves? You see check valves on gas lines. You see check valves on the discharge side of the pumps. You don't want the flow coming back into the pump, and then it'll just mess up the impellers inside. So there should be a flow direction. There always is a flow direction on a check valve. There's lots of different types of check valves. This one here is a swing check. There's a little door inside. The door swings up, the flow goes through, the flow tries to come back, it hits the door, it closes, so it can. If you go further into design, you'll realize there's certain places you can use a check valve. Obviously, you're not going to be able to use it on the vertical flow down because because of gravity, that's going to hang up. But there's different kinds of check valves that we could potentially put in the vertical down. It's not optimum to do that. There's different types of check valves. There's ball checks, there's piston checks. Sometimes what they do is they put a spring in here to make sure you just need a little bit more pressure in order to push the device up in order for the flow to go forward. So again, that's a swing check. Diaphragm valve. So in the hygienic world, the block valve of choice. Oh, what I did forget to mention, I'm so sorry. The ball valve. The ball valve kind of crosses between both hygienic and non-hygienic. This is an example of a hygienic ball valve. And I'll talk about the ends in a moment. We use this valve with steam. It's good with clean steam. This is a diaphragm valve. This is what you draw all the time for all of your hygienic services, your Wi-Fi, purified water, all that kind of good stuff. There's a diaphragm inside. When they install it, they actually have a preferred angle, so there's a weir inside, kind of like a little mountain that it goes up. However, if you tilt it at a certain angle, it depends on what manufacturer you have, there will be little to no holdup in there. When you have a pharmaceutical job, you're trying to minimize any holdup whatsoever. You can take the ends off, and when you're looking at it, and these are what we'll talk. I'll talk about them in a moment, but let's go over here to pipe symbols. So pipe, we talked earlier about small bore piping, and when we have small bore piping, we can do a socket weld or a threaded for our carbon steels. Socket weld is, I'll tell you what that is in a moment. So this here's my piece of pipe. This here is a union. I just put it in here. Actually, I have to back it up a 1/16 of an inch, or an 1/8 of an inch, sorry. And they put a fillet weld around here, and that's my socket weld. This is a lock ring coupling, isn't it?
Yes.
So I was trying to keep things simple for today, but this is the only piece of pipe I had. So I was telling you earlier that socket weld and threaded are the main ways we put pipe together for small bore piping. This here is a fancy mechanical coupling. It's called a lock ring, and they actually just have a clamp that presses down on here, down on the piece of pipe in order to make a secure joint. Right, so this is a socket weld connection. Just imagine this was threaded inside. They would thread the pipe, and they would just thread this on. This here is a union. You'll see unions a lot of times around steam traps on jobs. I didn't write that symbol down, but it's a little line, a long line, and a small line after it. What it is, if you need to break a piece, so again, this is a mechanical joint. So this here would be socket welded here. This is socket welded here. However, this is an external thread, and we can break it apart. So that's what the advantage of a union is.
It's just nice around a piece of equipment that you have to take out. If you have an all welded system, you can't really take it apart unless you have something like that or a flange.
All right. We can just close that. I don't have pipe that would, well, this is plastic pipe, but imagine it's carbon steel. This is an elbow. Same idea. It's a socket connection. So butt weld we kind of hit on earlier. It's where you have two pieces of pipe. There's an angle. It's actually 37.5 degrees. They put it together and they weld it together. Fran's husband actually provided a lot of this equipment. This here is a flange, but this end here is a butt welded flange. So the pipe would come in here. It would be prepped, and then they could weld it to it. So we'll talk about flanges. Like I said earlier, if we're going up to a piece of equipment, we rarely ever weld to a piece of equipment. We want to be able to take the piece of equipment out, obviously, put it back in. So usually we have a flange connection. This is a flange. What you would do is you put a gasket on the face of the flange. This is a raised face flange, by the way. Sometimes you see RF next to it. There's a little bit of a piece there. You put the gasket here, you put the mating flange up, and you bolt it together. There's 4 holes for this flange. The hole number increases as the sizes get bigger. The holes always straddle the center lines. I'm not going to pass this one around just because it's so big. Okay, so this was more for the non-hygienics, these guys. For the hygienic, we rarely use flanges for hygienic services. It's just a little more dirty. So what they have is they have a tri-clamp or a hygienic clamp connection. So it's like the flanges for the pharmaceutical industry. So what it has, instead of a flange, we have a ferrule end. The ferrule end could be on the end of the valve. It could be on this piece of equipment. It could be on the end of a flex hose. This is a flex hose. This here is our gasket. We hook it to the other side of the ferrule. And this is our clamp. This is a quick coupling. It's a wing nut style.
Need an extra hand. Here,
You may be more
throw it over
familiar
here.
with those fittings. They are used in the beer industry. When you go to a beer crawl or something, you'll see that the vats that they have, they all break down. And what they do that for is for cleanability. They can take this, if you take a look at your brewery, and you see the configuration of piping they have, it'd be very difficult to clean it unless they can take it apart. So they can break it apart with dry clovers and have it cleaned or heated. A lot of what they do in pharmaceuticals is based on them having a clean one.
actually,
Got it.
all of our BPE, ASME BPE is the governing body for these hygienic fittings and installations and things like that. But everything was based on dairy and breweries before. On the other end of that hose, you don't need to give it back to me, but this is a high pressure clamp. So there's just two different styles of clamps there. This one we'll use more. We definitely use it on steam, but those people like to have those because they're a little easier to install when you're a little more agile than me. But if you have to unhook and hook things frequently, these are the flex hoses. So if we have a portable tank, sometimes we'll have chilled water going to the portable tank. They'll need to take it off, take it on. That's why you would have the quick coupling there. That's why you also would not want it welded, because then how are you going to take it on and off?
So the quick coupling, there's really only one side there. There's a body and a stem on the end near Gina. You would pull that back and you would put that on the stem, and you would have like a dripless connection there that you could do pretty quickly. Fortunately, you only have one side of it.
Yeah.
But doesn't give you the full effect of it, but you'll see that a lot at your tanks, like Noreen said.
This here, back to the previous slide, is a Y strainer. And this guy here is a Y strainer. You look inside, there's a screen, and what we would do, this would be sitting in line. Whoops, it would help if I put it the right way. Here we go. So the pipe goes here, pipe goes here. What you would do here is, you could just put a threaded plug there, and when I need to drain this, so pretend those valves aren't there, I would shut this, undo this, and just drain it there. The two of us are a little confused why this is welded, because usually you can
I'm not confused, it came from my garage.
Usually you unscrew this nut to pull the screen, to clean the screen out. So pretend that you can get this off.
So you can see the position it's in relationship to the pump, is it's on the inlet side of the pump, because you can get things during fabrication and even during the use of the plant that are gonna end up getting into the pump and screwing the pump up. So it's there to protect the pump. You'll notice that there's a butterfly valve that she's got shown there, and then there's the strainer, and then there is the small drain valve there. So if you think about it, that system could be pressurized. So when you isolate it, you end up relieving the pressure in there, and then you end up doing a service on that.
So we prefer not to just put a plug here. And what Steve was saying is exactly what we show here on the P&ID. We would just have a little piece of pipe. A little piece of pipe is called just a nipple. We put a threaded nipple in here, put a ball valve here, and then put a plug on the end of the valve, because then we can just take the plug off and then open the valve. And then if we need to shut it off, we can shut it off very quickly.
If you don't relieve the pressure on some of this stuff, you start loosening it up, it becomes a little invasive. I've been at a plant where, at Philadelphia Electric, when I worked at Easton Station, where they realized the problem, and they saw a piece of insulation flapping in the operation, the grand hall, basically. And they traced it back to a position that was leaking about 100 feet away. And it was steam that was actually shooting across there that shot something through the wall. So you can see that if you don't do your maintenance on these things right, isolate and all that type of stuff, you can be in a bad situation.
Only because I think I want two other things to talk to you about. We didn't address them here, but steam, these are steam traps. You usually see them inside of a square with a T on top. They're just like the check valve, just like a lot of things, there's different types. This is a thermodynamic trap. What happens is the steam goes in, again, your flow direction, the steam goes in, there's a cap here that it'll kind of hover on top of the cap, and when it becomes condensate, it goes down. We'll use these a lot on the ends of lines. So the steam, we always want to keep steam in the line. And what the steam do when it cools down, it becomes condensate. Well, now we have slugs of condensate hanging out with the steam, and the steam's going to be cooled down more. So we're trying to rid the condensate out of the steam as much as possible. When you'll see a steam line, you'll see some drops, and there's some drip legs or dirt legs, trying to get rid of any of the condensate, to keep just live steam in that mean. Well, the problem is when you drop the condensate, you're also going to have a little bit of steam in there too, and you don't want to discharge any live steam downstream to a drain. So this is just ensuring the fact that any live steam that's left in there is going to be becoming condensate after that. That's why Fran and I are very adamant on our P&IDs that it's still considered steam through and including from the trap and upstream. And So a
Yeah.
lot of people like to argue with us. They say, "Oh, as soon as it leaves the steam main, it's condensate." I'm like, "No, it's not. We would like it to be, but so this is
Yeah, from a quality standpoint, that's one of the things we're trying to get into people's head. And if you see those types of things too, and you can make that point, that's even better, you know, catch it early.
So anyway, so again, this is a thermodynamic steam trap. This here is a floating thermostatic steam trap. So there's a little ball, kind of like in the back of your toilet, that sits in there, and that rises when condensate comes in, and actually the ball would be sitting against here, I think. I don't even know if the ball's in there. Oh. This is an FNT. There's
It is an
something-
FNT, it's an FNT 15.
Okay. Anyway, so it's when the condensate comes in, there's no rocket science here.
The
When
float.
when it fills with condensate, the float goes up, the water goes out. So this seems very heavy. This is cast iron. It's not that heavy. It's a lot lighter than these things. So that's why when we choose materials, we're choosing it for the application. We're choosing it for economics. A lot of places don't use cast iron. Refineries don't go near cast iron. Cast iron has a limit as far as your temperatures and things like that. But there's a need for it also. They don't weigh a lot. So what we went over today, so Fran went over as far as we have two major indices. We have an installation index, we have a service index. Now the service index we have hygienic and non-hygienic. And then I went through the material spec. So the material spec could have one service in it, it could have many services in it. But one thing your job will have is your job will have many material specs. We have 26 material specs on BMS. I think they're trying to add more. So you're going to see BBGO1, and 25 more. So the only other thing I wanted to show you, and we didn't really talk about it, but this is an OLED. So a lot of people don't understand or just don't really think about. If you have a pipe here, and we have to have a branch coming off here, this has to join to this one way or another. So if it was size on size, if this was a 6-inch line and this is a 6-inch line, we would put a T there. In the back of our material specs, let's see if I'm right here. Yeah. There's actually a branch chart that will tell you that. So typically, size on size and size one size down, we'll use a T. The thing is, T's get very heavy, adds money to the job. And then on small sizes, we'll use an OLED. This is actually a thread-OLED. So this will sit on the pipe, cut a hole in the pipe. They'll put this on here. This pipe's a little small. They'll do a full penetration weld here, and then that will be our branch fitting. The other option is we can actually cut a hole in the pipe, put the other pipe in here, and do a fillet weld. So that's the cheapest way. And I think that's really about it. This is just a coupling, a socket welded coupling. So if we have a socket welded system instead of a threaded system, we have to put the two pieces of pipe together that are small, 2 inches and smaller. We would put this on one pipe, this on the other. We would do a fillet weld on either side. There's another. Does anybody, this is very, very high level, but I think hopefully it explains some things.
Hopefully something was useful to you today, because a lot of times, you just feel like you're just making the marks and not really maybe getting the full picture. I know we feel that way at times with our job, so I'm sure you guys feel that way with yours. But we'll keep the samples over at our desk. You're more than welcome to stop by. You're always welcome to stop by and ask a question. If you see something on a P&ID and it just looks fishy and you're uncomfortable going to the process engineer and just want, am I on the right? We get those questions all the time from, Anthony and Ginny and Vida. They'll come by and they'll, something just doesn't seem right here. So feel free to stop by. We're more than happy to help you. That tool Maureen pointed out, we don't actually issue that a lot, but we'd be more than willing, if that helps you just have a sanity check on a job. I want to see all ball valves on this particular spec in this size range, and I'd like to just have that here as a little tool so I can make sure they're following what they should be following. We'd be more than happy to put those things together for you. So don't be afraid to stop by. We're always willing to help you, show you what we know, and
So just in your understanding of how this all ties together, when you're working on a job, I'm sure you all have access to JPI for that project. Usually these are located in most of the projects under global, and then under either client documents or under specifications.
Yeah, the general place specifications.
And you can actually go in there, the specifications, the two service indexes that they will have are the 15-201 and 101.
Correct.
101 is for the carbon steel stuff, the 201 is for the clean stuff. So if you went into there, you could take a look at those service index, and they will reference you to the other 1,500 number specs that are in there, so you can kind of just work around through there and understand how these documents all kind of work together. And again, it gets you kind of an introduction. I don't want you guys always just doing red to black. That's a shame. You should understand what you're putting down, and it'll be a little more interesting too.
Yeah,
What
like
kind of questions do you have? There's one.
Yeah, well, first I just wanna thank you guys for putting this together, like I wish we could do these things more, cause we see symbols all the time and we don't necessarily know what we're looking at, so I appreciate it. And then my other question is, I was just curious how you guys got into it.
Tammy just asked me that the other
Yeah, I'm
day.
just curious.
Fran will say it was a weak movement.
Cause it's very specific.
Well,
What
so
you
I
doing?
went to school for chemical engineering, and when I came out, I got a job in the piping group at Siegel, which is a company that Jacobs
Right.
acquired.
Okay.
And I was a piping engineer in that group, and was in that group for 9 years. Left for a little while and had my kids. And they had somebody who had been doing specifications for them, but they wanted to grow into the piping engineer role. And I was looking for a little bit more of a family-friendly role. And, you know, I was totally into doing this type of work. So that's how I got it, kind of a roundabout way of coming into a career path. But it used to be a little bit more of a simpler job when I started, and it is extremely complicated now, just because our, you know, we're servicing global clients now, getting into much more chemical-related projects than maybe my first, 10 years of experience had been. So
So you were doing the engineering and the design first?
correct, yeah, and then came about into this side of things, so.
I've only been doing this. I worked at Foster Wheeler for 4 years.
Also did quite a bit with procurement related.
Oh, yeah, well, I did
She
that,
was
yes.
project in China, did all that stuff.
Yeah, yeah.
And she has done some design in PDMS for you?
I did PDMS when I guess, God, probably with Rachel or somebody, yeah. 13, 14 years. I was 4 years at Foster Wheeler. Didn't want to live in North Jersey anymore. 4 years at Fluor. That was just as the office was closing, and then I came here.
But if any of you are interested, if you thought, I'm interested in being involved more in the material side of things, please let us know. I mean, we always are looking for people who, want to go that route.
Mhm.
It's not really a glamorous role, and you have to be somebody who likes to research and do a lot, and very detail oriented, so.
Yeah, if you look at all these, and it's not, I should say all these, and I can't even find it, there's a code for every one of these, and you have to know the codes. So, and ASME BPE seems to be, since it's fairly new, I think the first one came out, 89, was it 80? No, or
98.
98, that was your version. They're really revising it a lot, whereas this is, flanges go under ASME 16.5, that's been around, I don't know, at least since the 40s or before that, so there's not many changes to that specification.
Yeah, so that, in the life of our career, that's one very exciting thing that's happened, because that's basically went from having no standard to having a very
Yeah, like, is there
well-written standard.
some sort of certifications that you have to have, like, Jacobs is saying to the client, this is what you should be using, or is it just, well, no, you're a professional engineer, like, is there any sort of?
For material engineering? No, not necessarily. I mean, the design is, I guess, signed off by the lead engineer for the
Right.
project, and that
Gotcha.
would cover our work as well as,
Gotcha.
the design.
So you wouldn't necessarily have to be, would you have to be an engineer?
You don't necessarily have
You
to,
do-
basically,
I
they're
would
taking
say
a bunch of
no,
things
you-
that are available to you.
Yes.
These standards and everything, they're standards.
Right.
They just know them and they know where to apply.
Correct, right,
And-
right,
and
right.
Just historically, when I joined, there were non-engineers, whether, they might not have been in the piping department, but non-engineers, and say the electrical department, they also have a specification person, and they were, they were preparing the documents for the contractors.
They also do a couple other things. They're involved in line lists that we do.
Right, so the line list is a tool, I don't know that you guys do a lot with that, but I guess as things change over the next few years, you're probably more aware of it than a lot of us even are. Intelligent P&IDs and how you can
Right.
get a lot of that information that we have the grunt work of doing manually now out of the system. And those are great, they're needed in the field for the contractor, but they're also like a great quality control check for us, because then we can put filters on and say, process engineer didn't get that spec right, or the insulation thickness isn't right. But, so those things are come in handy, but, you know, there'll be times where, you know, one of you may get pulled in to do that type of work, and that's, you know, real helpful work, and gives you a little bit of a different appreciation for what you're doing, what we're doing.
This office doesn't see, I support the Mount Laurel office also, so they have some crazy high pressures, but, and I don't do a lot of work for them, but I've worked with the guys back at Fluor, so they seem to call me a lot. But again, we put the filter on, and that's when we know, like I said, this is a class 150 flange. I guess this would be another lunch and learn, but a class 150 flange has certain ratings based on that code. The next class will be a class 300. So, you know, just because we go to the code so much, we know what the pressures that each flange can handle at each pressure, at each temperature. And when I put the filter on, I'll find things that it's exceeding the flange rating. So I'll say, no, you can't use BBGO on there. You need to find another spec.
So we didn't even touch on, we talked a lot about carbon steel, some stainless steel, she showed some plastic, there's copper, there's a lot of other materials out there that you might come across that were on that one list. Cement lined ductile iron, things maybe you come across for fire protection.
Right.
Or for civil, if you do any of the civil work.
Double containment.
Yeah, double
maybe,
containment, yeah.
in
So
case you have spills.
feel free to
So
just,
there's all kinds of
if
stuff.
there's stuff you know, weren't exposed to today, you wanna know more about. The internet's great, but come by, if we can help you, we will.
Yep. It's all, I took Ty down there. He thought I was crazy when the first couple. Was it you or was it Tim? Or what was
Pat.
Pat. To the stairwell because it's all Victaulic piping. So we talked here about this being a socket weld connection. Well, another way to put pipe together is they actually have a groove here, and you put a clamp. So that's how it's pretty much everyone knows it as fire protection. It's great. Again, there's no welding, so you don't need a certified welder to put it together. But we can also use it for chilled water and things like that. I'm just not.
Don't be alarmed if Noreen has you following her into the bathroom. or anything.
No, they do that with fire
Okay.
protection.
No, it's
In
good.
the stairwell.
You can see a PI there. You can
Yeah.
just go up the
Yeah.
stairwell. Start looking. You'll see. You'll see. Now you know this is a 90.
That was, yeah, I know.
So does anybody have any questions or things you've seen that you're just, you know, wanting to ask here, or? No? Okay.
We're pretty approachable.
Nothing? Nothing at all?
I like seeing the actual valves because like we use it, and some of it I just go, oh, that thing.
And I don't think we appreciate
I
it.
mean, I know what it is, and I know like where it